spectroscopy is part of the exam.
It's a few questions.
Sorry?
It's a few questions. It's not a huge part, but it's a few questions.
So I can just
make
basically
sure that
link
you
it
looked
up,
at it.
there's no one really knows all that.
Okay, who wants to ask the first question? Yep, just a second. I just want to double check again what this thing is we're going to take to get to the end. I think it is, but yeah. Okay. All right. Yes.
Can we go over half-lives?
Half-life. Sure. So. Wait, is that under chapter 8? Or, I mean 7? Is that right? Or which one is it?
8.
It is 8. Yeah. All right. That's pulled up the wrong one here. 8. Okay, so remember the idea of half-life is if you've got some radioactive sample, then the half-life is how long it takes for half of those nuclei to decay. So, in other words, after one half-life, half the material is left. After 2 half-lives, how much of the material, the original material is left? Half of half, right?
So
a quarter, 0.25, right? After 3 half-lives, half of a half of a half, an eighth, or 125. After 4 half-lives, a 16th. Every half-life that elapses, you get rid of half the material that was present at the beginning point of that half-life, so to speak. So in other words, it's a continuous process. So after 1 half-life, half the material is decayed. After 2 half-lives, 3/4 of it is decayed. 1/4 of it is left. After 3 half-lives, 7/8 of it has decayed. 1/8 of it is left, and so on. Because you keep getting half of half of half, depending on how many half-lives you have. So the example from the book, this plot here is potassium 40 that decays into argon 40. So if a rock solidifies, because argon 40 is a gas, it won't have any argon 40 in it initially because when it was molten, all the gas would just bubbled out of it. There won't be any argon 40 to start. So this is a particularly nice, convenient thing for scientists to use. Other radioactive decay schemes are trickier. You can still use them, but they're trickier because you have to have some way of estimating how much of the material was in the rock to start with of the daughter products, of the things that are the results of the decay. But in this case, you can assume that all the argon 40 trapped in the rock was due to the decay of potassium 40. And so here we have fraction of isotope. So 100% of the isotope potassium 40 of the original sample will certainly be there when the rock solidifies. That's when we're starting the clock, so to speak. After 1 half-life, half of the potassium 40 remains. After 2 half-lives, then 1/4 of the original potassium 40 remains. Notice that half of the material that was there at the start of the second half-life, so to speak, is decayed during the next half-life. During every half-life that elapses, 1/2 the material goes away. It's a continuous process. So in other words, you could say how much material is left after 3.16 half-lives. And it's an easy thing to do on a calculator with the appropriate formula. On the graph, you could say, okay, here's about 3.16 half-lives. So this fraction, whatever this is, remains something like 0.2 of it or something like that. Did you have a question?
Yeah, as the potassium is decaying, is it becoming argon?
It's becoming argon. Potassium 40 decays into argon 40. So originally, there's no argon 40 in the rock, but as potassium decays, it's turning into argon 40. And so that's what makes this system convenient, is that scientists can measure how much argon 40 is in the rock, and that all was initially potassium 40. So they can always figure out then from how much potassium 40 is still there, plus how much argon 40 is in the rock. They can add those 2 things together, and that tells them the amount of potassium 40 that was initially in the rock. And so on this graph right here, what is the half-life of potassium-40? So after one half-life, half the material is left, how much time is that?
1.25.
1.25 what?
Billion.
Billion years, yeah. So this is 1.25 billion years for the half-life in this particular case. So if you measured the amount of potassium-40 and argon-40 in the rock, and you discovered that 1/4 of the potassium, of the originally present potassium-40 was still there. 1/4 of it is still there, and 3/4 of it has turned into argon-40. Then how many half-lives have passed?
2.
2 half-lives have passed because a quarter of the material's there, so therefore 2 half-lives have elapsed. How much time is that? Well, each half-life is 1.25 billion years, so 2 half-lives is 2.5 billion years. So the rock would be 2.5 billion years old at that point when a quarter of the material is left. And so that's what it comes down to. In other words, if you know what fraction of the original potassium-40 is still there, you can figure out how many half-lives old the rock is. Given that the half-life is 1.25 billion years, you just multiply the number of half-lives times 1.25 billion years, and that is the age of the rock. And I will be nice and make it a nice even number if I give you a problem like this. In other words, if you were physics majors or whatever, then I might say something like, 0.743 of the material is left, and how many half-lives you need a calculator to do it. But in this case, you can just read off from the graph, or you just know after 2 half-lives, a quarter of the material is left. So you go to where it says 1/4 of the material is left, that's 2 half-lives, 2.5 billion years.
Will the rock ever die?
You mean, will it ever run out of potassium-40? It'll take a long time. So in principle, well, not in principle, I shouldn't say that. If it weren't for the fact that it is actually individual nuclei of potassium-40, mathematically speaking, you never get to 0, because no matter how many times you cut something in half, mathematically, there's still some of it left. But this is individual atoms of potassium-40. So for that reason, eventually you get down to the point where, there's only 4 potassium-40 atoms left in the whole rock. And then roughly 1.25 billion years later, one of them is decayed. Now there's only, or 2 of them are decayed. Now there's only 2 of them left. In other words, eventually the very last one will decay, but that'll be billions and billions and billions and billions of years from now. So a really long time. But eventually, the entire sample would have decayed. With something with a half-life this long, it would take more than the current age of the universe for all of it to decay. But if the half-life was 6 minutes, then after some reasonable amount of time, all of the material would actually eventually disappear, because of the fact that it consists of individual nuclei. It's not infinitely divisible. Yes?
Well, it's kind of what formula are you going to use for the second law? You use multiplication law or division law?
Doesn't matter. But what I want you to do is understand that acceleration and force and mass are related. That the acceleration is the force divided by the mass. But, also force is mass times acceleration. But I like acceleration equals force over mass because it emphasizes the causality. So any more questions before we move on to something else about this topic? Yes?
So I just want to make sure I'm clear. So the
Yep.
term half-life sort of has 2 implications as far as this is concerned. One being the half-life of whatever it is that you're observing, and then the second thing is the number of half-lives after that, right?
So the half-life itself is the time it takes for half the nuclei to decay.
Right, and then
No matter when you start the clock, no matter when you start, after one half-life beyond that point, half of how many atoms were there when you started the clock, so to speak, will have decay.
And that's one figure, and then the second figure is every half after that, or every half calculation after that is also.
I mean, I think I see what you're saying, but I would say the half-life itself is literally the time it takes half the atoms to decay. Now, how do you use that fact you use that fact by saying, well, then after 2 half-lives, you'll have half of the original material left, a quarter of it after 3, an eighth of it after 4, a 16th of it, and so forth. So in other words, that second part you're talking about, that's not the half-life per se, but you're using the half-life to figure out how old the rock is. You figure out how many half-lives have elapsed from what fraction of the original material from when the rock solidified. Because the age of a rock is defined to be how long it's been since it solidified from a molten state. Then from whatever fraction of the original material, the original radioactive isotope was there when the rock solidified, you figure out how many half-lives have elapsed. You multiply that by the amount of time that is a half-life, 1.25 billion years in this case, that is the age of the rock. So there's the issue of what is the half-life and then how do you use it to figure out the age of the rock. Okay, any other questions about that? Okay, so let me ask you another question. Yes?
Can we go over tides, like the,
Yeah, so
in general?
lunar tides, solar tides, all that sort of thing, yeah. So, right, that is chapter 4, yeah. Let's see. Yeah, we didn't talk about it in class, so I don't have a slide for it here, but let me just go into.
So it won't be on the
No, I didn't say that. The fact that we didn't talk about it in class, I have you read the book, and so it's perfectly reasonable to say that you should learn something by reading the book too. So let me pull up the relevant images and I'll talk about that. So I've got them in my Google Drive here. I have them all. Instructor resources let me have all the figures from the book. So I just got to find it here. Textbook figures. Then the Cosmic Perspective, Chapter 8, or 8th edition, and Chapter 4. Okay. So, tides arise from the fact that gravity decreases with distance. The further you are from something, the weaker its gravity is. So here's the moon. It exerts gravitational forces on Earth, but the side of the Earth that is closer to the moon has a stronger force of lunar gravity on it than the side of the Earth that is further from the moon. And the effect of that is to raise a tidal bulge that essentially points towards the moon. It's counterintuitive. It's hard for even physicists to fully grasp this. It's subtle. But, so I'm not going to worry about having you explain in detail exactly how this arises. But what I want you to know is what it ends up doing is raising a tidal bulge both on the side facing the moon and on the side away from the moon. There's an outwards bulge both on the side facing the moon and the side facing away from the moon. In a sense, you can kind of think of it as the center shifts more than the left edge does here, and the right edge shifts more than the center does. So overall what happens is you get a tidal bulge along the line towards the moon, and it bulges outwards on both sides,
So
not
is it
just the
equal
side
on both
facing the moon.
sides?
It's equal on both sides, as a matter of fact. Yeah, the tides are, the tidal bulge height is equal on both sides. Now, this is greatly exaggerated. The tides are, on the order of feet in height. This makes it look like they're hundreds of miles or like 1,000 miles tall or something like that. But it's just exaggerated. It'd be trouble if it were. It's just exaggerated so that we can actually see it. And because water can flow, the oceans are affected by the tides more than land is. There are actually land tides too, but the land tides are only something like, I think it's like an inch or something like that. The ocean tides are feet, land tides are more like an inch. So this is kind of representing the ocean tide, and the idea is, as Earth turns, if you were on a shoreline, so that you actually will see this, then when you rotate into the bulge is when you have a high tide. So in other words, how many high tides a day will there be? Two, because there will be one when you are on the side of Earth facing the moon, and one when you're on the side of Earth facing away from the moon. So, in other words, at high tide, then you'll generally see either the moon is high in the sky for you, because you're on the part of the Earth that's lined up with the moon, or the moon is invisible to you because it's below the horizon on the other side of the Earth, essentially. So there's two high tides a day, and there's also two low tides a day. The low tides are here and here, where the height is a minimum. Yes?
If you were, like, there's oceans on those sides too, so it like the tidal, I don't know exactly, but like would the bulge be flipped too, like when the moon's there?
So yeah, so in other words, as the moon orbits us, the direction of the tidal bulge follows the moon around. Yeah, the tidal bulge follows the moon around, yes. Because the moon is orbiting us. The thing is, the sun also raises tides. They're not as big as the tides raised by the moon. Even though the sun's force of gravity on Earth is actually a lot bigger than the moon's force of gravity on Earth, it turns out that the tidal force depends on, I think it's the sixth power of the distance. So as a result, it turns out that the tides due to the sun are smaller than the tides due to the moon, but they both raise tides on Earth. And so the strongest effect will be when when the sun and the moon are both along the same line as seen from Earth. So in other words, at new moon, when the moon is between us and the sun, you get especially high tides because the line from Earth to the moon is also the line from Earth to the sun. And at full moon, you also get especially high tides because, again, it's all the same line. The line to the moon and the line to the sun are essentially a single line. So that produces the highest high tides. Anybody remember what are those called?
Spring tides.
They're spring tides. It's kind of the water springing out, you might think of it as. So those are called spring tides. And neap tides, the weakest tides, are when the line to the moon is at a right angle to the line to the sun, because then they are counteracting one another than reinforcing one another. So you get neap tides when there's basically a 90-degree angle between the sun and the moon in the sky. Well, when is that? When is the moon about 90 degrees away from the sun in the sky? What phase? Quarter phase. First quarter, third quarter. So first quarter and third quarter are associated with the weakest high tides. New moon and full moon are associated with the strongest high tides. And that's basically what I want you to understand. I want you to understand that there's a tidal bulge equally large on both sides of the Earth, not just one side, and that you get the strongest tides when the sun and the moon are cooperating with one another, so to speak. They're both along the same line. That's new moon and full moon. And you get the weakest tides when they're working against one another, when the moon is at first and third quarter, because it's about 90 degrees away from the sun in the sky. Okay, any other questions about that? Yes?
Neap.
N-E-A-P. Neap, yes.
Do we know about tidal friction?
It turns out not to be on the exam. I was told.
What would you say?
Tidal friction.
Oh,
tidal
tidal
friction.
friction.
Yeah. Probably should have said sure and then gone into it, but I'm not. How stupid of me, I should have said sure and then explained tidal friction right now. I'm such an idiot. I'm sure you guys are all mad too. It's like, damn it, I wanted that to be on the exam. Yes?
What's the format? Like number, multiple choice?
It's almost all multiple choice, but there's a couple of, there's gonna be one, as I've warned you basically, that is based on
Plans, right?
the planet thing, right? So in other words, based on this slide where I give the masses of the planets in terms of the Earth's mass and their distances from the sun, all that good, densities. Basically with the densities, for the terrestrials, it's about 5 times the density of water. For the Jovians, about 1 times the density of water. And of course, you want to know that Jovians don't have solid surfaces, whereas terrestrial planets do, all that kind of goodness. So there will be an opportunity for you to fill in a table of the masses and distances and so forth of the planets in terms of Earth's mass and distance. Remember too that I want you to know the Earth's mass in kilograms. It's about 6 trillion kilograms, 6 times 10 to the 24. I want you to know that it's about 8,000 miles or 13,000 kilometers in diameter. And I want you to know that it's about 100 million miles or 150 million kilometers from the sun. And then the other planets, I want you to know in terms of Earth's values. In terms of Earth's values. Yes?
Well, how many kilometers from the sun did you say it was?
About 150 million. You can give it in miles or kilometers.
Where is
100
that on
million.
where is that on the thing?
It's on there somewhere. Yeah, Earth's diameter is about 13,000 kilometers, 8,000 miles. Earth's mass is about 6 times 10 to the 24 kilograms. And somewhere I mentioned that an AU, or maybe not on this slide, but somewhere I mentioned that an AU is about 100 million miles. Is it on there? I think it's. Is it? Let's see.
That's Earth.
Uh,
The last thing,
the last thing.
like
On the bottom there.
Yeah.
Oh yeah, there we go. Okay, I knew I had it somewhere. Yeah. 150 million kilometers or 93 million miles, but you can say 100 million miles if you prefer. I don't care. Close enough. I want the numbers to be, it's not important to know that it's 92.9 million miles or whatever. Just it's about 100 million miles. It's good enough. Yes.
Alright, so 2 questions. So it's not sufficient to say 1 AU. I can't just.
No, because I want you, for Earth, I want you to know what it actually is. For the other planets, you can put it in terms of the values for Earth. So in other words, for Jupiter, I just want you to say 5 AU. I don't want the number of kilometers or the number of miles from the sun.
And also,
But for Earth, I do want you to know the actual number of miles.
you said something about density being 5. So is
Yeah, for the terrestrial planets, the densities are all around 5 grams per cubic centimeter. For the Jovian planets, they're all around 1 gram per
So
cubic
this
centimeter.
is 5 for terrestrial, 1 for.
Yeah, basically, yeah. Yeah, the terrestrials are about, on average, 5 times denser than water, and the Jovians are about the same density as water on average. There's variation in there. The point is, I want you to have a basic idea of these quantities, not memorize them out to 7 decimal places or something. I don't have them memorized to 7 decimal places. That's just silly. But you should know basically what the values are. If I want it out to 7 decimal places, I can look it up. That's what Google's for. In ancient times, I actually looked them up in books. Who does that anymore? One thing about the internet being available these days, you guys probably can't even relate to this, but man, when I was a kid, you'd like think of a song and you're like, oh, who sang that song? Or what were the lyrics to that song? And it would just drive you nuts. Now you just type in the first 3 words in Google and you see everything about it. I do not miss the feeling of, man, I can't remember. Not like take you 2 days, like you hate the world because you couldn't remember that. Drive you nuts. Okay, who has another question? Yes?
Okay, can you go over nebular theory?
Nebular theory, that's a lot, right? I mean, you're basically saying,
just all
can we
just-
go over chapter 8? Right? So, I guess, kind of, like, can you be a little more specific? Like, what do you want to know? Certainly, you want to, it's important that we had these properties of the solar system a successful theory needs to explain that we saw in chapter 7, and then chapter 8 we actually explained them, right?
Yeah.
So you certainly want to be able to say, okay, why are all the planets orbiting the sun in the same plane? And it's because they formed in a disk. And so they are orbiting in the plane that that disk had. Things like that is what nebular theory is all about for us. Certainly, the very idea of nebular theory is that the sun and planets form from the collapse of an interstellar nebula, a big cloud of mostly hydrogen and helium gas with a little bit of other elements mixed in, about 2%, that collapsed and spun faster and flattened into a disk. The planets formed in the disk. So in other words, what you want to do is you want to go through patterns of motion amongst the large bodies, and then how does the solar nebula theory explain it? And so on and so forth. I've got a whole series of slides here. The existence of two types of planets, terrestrial planets close to the sun, Jovian planets far away from the sun. The solar nebula theory explains this as follows, and so forth. I'll be happy to talk about that, but in other words, go over nebula theory. I don't know if everybody wants to hear me just do all of chapter 8 again, basically.
Fair enough.
But if there's a cry for it, yes, we want you to do chapter 8 again. I'm happy to do it. Or you can just ask me more specific questions. But recommendation: go to the chapter 8 slides on Blackboard and review these slides where I systematically go through the properties that the theory needs to explain and how the theory does so. It's all there, laid out. Yes?
You go with light and spectroscopy.
Okay, light and spectroscopy. Now again, I'm not going to do the whole tutorial in front of you, but on the other hand, if we go to the slides here for, which one was it? For chapter 4, is that the one? I put slides about, not chapter 4, where is that? Chapter 7? Yeah, chapter 7. I put some slides about light there. So certainly you want to know what wavelength is, you want to know what frequency is, wavelength is, the crest to crest distance, the distance over which a wave repeats itself is wavelength, the frequency is how many wavelengths pass by you every second, and the higher the frequency, the shorter the wavelength, and vice versa, because if the wavelength is shorter, imagine I'm standing here and all these waves are traveling past me. All light travels the same speed, 300,000 kilometers per second, basically. So if all three of these waves are passing by me at the same speed, clearly, if the wavelength is shorter, more wavelengths are going to pass by me every second. So the shorter the wavelength, the higher the frequency, and vice versa. And
Gamma and all that stuff?
I'm not making you here in this class. In 111, I make people memorize not the exact wavelength cutoffs because those are arbitrary, but there I make people memorize that it goes gamma rays, X-rays, ultraviolet, visible infrared, and radio from shortest wavelengths to longest wavelengths. In this class, we'll mostly be interested in visible light, of course, and then also infrared light and ultraviolet light. In particular, when we talk about the greenhouse effect, it's important to understand what infrared light is, and so we'll use that then. But I'm not asking you to memorize the names of everything in the spectrum, although you've probably heard them before. Everybody's heard of ultraviolet light, and everybody's heard of infrared light, and so forth. And then in the tutorial, go through the tutorial, and it talks about electrons jumping up and down between atomic energy levels. Again, I can talk about that if you'd like me to briefly here. I'd be happy to do that.
I'll just go through the tutorial, that's fine.
Yeah, go through it. Right. If anybody wants me to talk about atomic energy levels, I'm happy to do it. Absolutely happy to
Could
do
you
it.
go ahead and do that, please?
What's that?
Would you do that, please?
Yeah, okay, so I'm gonna pull up some slides from Astronomy 111, because there we do talk about it in detail. So, courses, Astronomy 111. Swirly swirly. Sometimes it doesn't lunge. That's not helpful. I have an internet connection. Apparently I do, okay? Now, I'm not going to spend obviously as much time on it now as I would if I were really doing it for class, because we've only got so much time here and there is the tutorial to work through. So if you haven't worked through that tutorial, do it. But anyway, when it comes to spectroscopy, the idea is that every element has certain wavelengths that it is able to emit and absorb. So in the tutorial, it talks about how if you have a hot light source that's dense, like a light bulb filament, then you get a continuous rainbow spectrum. If you break the light into its various colors using a prism, or what's called diffraction grating. If you have a hot cloud of gas, then, like in a neon sign, for example, then you get what's called an emission line spectrum. You get a spectrum, a spread, a plot of brightness versus wavelength, which essentially has a bunch of sharp peaks, and it's essentially zero in between. So in other words, if you look at the spectrum, you see a bunch of individual bright lines at specific wavelengths, specific colors, and everywhere else it's dark. And then if you have a cloud of gas in front of a hot light source, then you get what's called an absorption line spectrum, where you get dark lines in front of a continuous rainbow spectrum. And for any given element, there's a specific set of wavelengths that it is good at both emitting and absorbing. So if you look at the wavelengths of all the spectral lines that come from a cloud of gas, or are present in absorption from a cloud of gas, then you can figure out what elements are in that cloud. And you get to do that in the tutorial. They give you a few examples where they give you a spectrum. You turn on spectra of various elements to see what their spectral lines look like, and then you can compare and determine what the cloud is made of. Every chemical element has its own unique set of spectral lines. So only helium has these particular wavelengths of its spectral lines. And again, the same wavelengths show up in both emission and absorption. So for sodium, for example, there are two closely spaced in wavelength yellow lines that a hot cloud of sodium will emit. And if you take a cloud of sodium and put it in front of a source of continuous spectrum, you will see dark lines where light is missing because the sodium atoms are absorbing light at those particular wavelengths. And the reason why elements behave that way is because atoms, the electrons in atoms only are allowed to have certain energies, and they can absorb photons to move up in energy, or emit photons by moving down in energy, and they emit and absorb photons only of wavelengths such that their energies are equal to the differences in energies between various levels inside the atom. And so for hydrogen, for example, this is what's called an energy level diagram for hydrogen. The lowest energy the electron can have is called the ground state energy, and then there are various other energies that the electron can have that correspond to it being further on average from the nucleus, depending on how much energy it has. And the only wavelengths that hydrogen can emit or absorb correspond to energies that are differences in energies between these various levels. So for example, if I had an electron in this 12.8 electron volt energy level, and it gave up energy and dropped down to the 10.2 electron volt energy level, it would have lost 12.8 minus 10.2 equals 2.6 electron volts of energy, and that corresponds to a particular wavelength, which can be calculated with this formula right here. I'm not going to make you do that, but in other words, with photons, packets of light, the shorter the wavelength, the higher the energy, and vice versa. So again, work through the tutorial, and if you work through the tutorial, then you should know what I want you to know for the test. And there's a few questions on there, a few multiple choice questions on there that are based on that tutorial. Okay, any questions?
About this, or?
Yeah, about this or anything else? If there's no, are there any more questions about this? Okay. Okay, now some of them.
I have a different question.
Yes.
Is the uniform circular motion, I don't know if that's a theory, but is that related to kinetic energy and gravitational potential energy when planets?
So uniform circular motion isn't, I mean, it's not a good example of it, okay? But on the other hand, so in other words, if you have an orbit which is perfectly circular, then the planet's speed would stay absolutely constant as it moved around the sun, and its distance from the sun would stay absolutely constant.
But that doesn't happen, right?
Well, it could.
I guess Earth is close.
Earth is close, right. There are no planets, though, that completely meet that criterion. So what I would say is, sure, it would apply there, but in a trivial sort of way, because the kinetic energy would be rock solid, constant,
Right.
and the gravitational potential energy.
So the uniform
would be-
circular motion, just saying that when there's a perfect circle, there's also a constant speed.
Yeah, uniform circular motion would be motion around the circle at a constant speed. Okay, so question, if you're moving around the circle at constant speed, are you accelerating?
No. Or yes, you are. because
Yes,
you're-
you are, right? Because you're changing your direction. That's absolutely right. Because velocity involves both speed and direction of motion. And so when you're going around a circle, you're constantly changing your direction. So that is accelerated motion. What direction is the force needed to hold something in uniform circular motion? So the example I always like to give is you pick up your little sibling, swing them around. Now, as I swing my little sibling around, do I have to push out, pull in, or something else in order to keep them from...
Pull in.
Yeah, I got to pull in. So I have to exert a center-directed force, a centripetal force, in order to keep the kid moving around the circle. The force in uniform circular motion is directed towards the center of the circle. We call that a